In a previous video, we looked at the energy density in electric and magnetic fields. So now we will use those results to look at the energy density in an electromagnetic wave and the relation of the energy density to the Poynting vector. So an electromagnetic wave, as its name suggests, has both electric and magnetic fields. So our total energy density will be the energy density of the electric fields plus the energy density of the magnetic fields. Using the expressions that we had previously, we can write it as such. However, we can simplify this expression taking advantage of two relations. One is that for an electromagnetic wave in vacuum, the strength of the B field is related to the strength of the E field by B is equal to E divided by C. Remember that the B field is always the weaker field of the two. The other relation that we have is an expression for the speed of light in vacuum, which is C equals 1 over the square root of mu naught epsilon naught. Squaring both sides and moving things around, we get 1 over mu naught is equal to C squared times epsilon naught. So we can use both these relations to convert this second term into something similar to the first term. And so we have U total is equal to 1/2 epsilon naught E squared. That stays the same. And then here, 1 over mu naught becomes C squared epsilon naught. B squared becomes E over C the whole squared. And there's the 1/2. But we see that, oh, the C squared is going to cancel, and we're going to end up with, in fact, a term which is identical with the first term. And so our total energy density is epsilon naught times E squared for an electromagnetic wave. And being an energy density, the units of this are joules per meter cubed. Now, what is the relation with the Poynting vector? Well, let's start with the Poynting vector's definition. The Poynting vector, denoted by S, is 1 over mu naught times E cross B. Let's assume we're dealing with a plane wave, a plane electromagnetic wave. And so, for example, let's say we have an electric component and a magnetic component. The electric component is pointing in the I hat direction, well, plus or minus I hat, depending upon the value of the cosine. And the B field is pointing in the J hat direction. And the direction of E cross B will be I cross J, which is K. And so that is the direction of propagation of the wave. And true to that, we see that the arguments inside the trig functions are of the form kz minus omega t plus phi naught. It's a little hard to read over there, but yeah, same thing, kz minus omega t plus phi naught. Phi naught here is simply the initial phase. Omega is the angular frequency, k is the wave number, and the fact that it's kz minus omega t tells us that as time increases, z will also increase if you want to keep track of the same point. So in other words, this is a wave that is traveling in the positive z direction, which is good because E cross B is giving us k hat, which is the direction of propagation. All right, plugging in those expressions for both E and B, we get 1 over mu naught, E naught B naught, I cross J gives k hat, and then we have cosine squared kz minus omega t plus phi naught. So starting with that expression that we just wrote, the S vector is E naught B naught over mu naught times k hat cosine squared. But we can play the same tricks as before. We can replace 1 over mu naught with C squared times epsilon naught, and we can replace B naught with E naught over C, since this is an electromagnetic wave. Collecting all that, we get that S is C times epsilon naught E naught squared times k hat times cosine squared kz minus omega t plus phi naught. All right. Now, it turns out that we will often be interested in the time average of the Poynting vector. What do we mean by time average? Well, we take the Poynting vector, we integrate it over one time period, integrate with respect to time, and then divide by the length of that time period. What is the effect of this operation? Well, it doesn't have to be the Poynting vector. It could you can talk about the time average of any time-dependent function. So, for example, supposing you had some function of time that varied like this over some time period, capital T. Then what this time average does is ask if we could replace this time varying function with just a constant function such that the area under the curve is the same. Well, that constant value is the time average of the original function f. So you can see that basically what we have done is this integral calculates the area under the curve, and then we divide it by the length, the time length of that interval, and we get this average value for the function. And so this area under the curve will be the same as this total area under the curve here, but it is now, instead of varying with time, is just a nice constant average. So we are going to do the same thing for this S vector, but we see that the only time-dependent part is this cosine squared. So our time average of S, well, we pull out all the constants, and then we have the time average of cosine squared. But it turns out that the time average over one full time period of cosine squared is just 1/2. So this is our time average of the Poynting vector, c epsilon naught e naught squared k hat over 2. Looking at the units, we see that, okay, well, c is a velocity, well, speed, so that's in meters per second. And then epsilon naught E naught squared, we know, is an energy density, so that's joules per meter cubed. And so the units are joules per meter squared seconds, or joules per second divided by meter squared. And so this gives us an interpretation of what's going on. Joules per second, we know, are watts. So these are watts per meter squared. And so this quantity, the Poynting vector, is talking about the power per unit area, watts per meter squared, which you can also think of as the energy flow per unit area per unit time, right? Joules per meter squared per second. So just looking at the magnitude of this time average, ignoring the direction, we have the time average of the magnitude of S is c epsilon naught E naught squared over 2, which is called the intensity of the EM wave, which we sometimes denote by a capital I, unfortunately. So don't confuse intensity with current. You have to figure out by the context which one we're talking about. But yes, intensity is the power per unit area. So when we talk about the intensity of a light source, it's telling us something about how much power that source is outputting and how that power is spread over area. Notice from this expression that the intensity is going to be proportional to the square of the electric field. Talking a bit more about intensity, we can imagine that we have a light source, a little point light source. You can imagine, say, a light bulb that is emitting power in all directions. Since it is a point source, if you imagine the light blinking on and off, what will happen is that you will have a spherical wave of light, a pulse of light in the shape of the surface of a sphere, that expands as time passes. Since the light source has a certain power output, a certain amount of energy it is giving off per second, what we see is that the intensity, which is the power divided by the area, is going to change as we move further and further away from the source. When we're very close to the source, the power is spread over a relatively small sphere, right? The area of the sphere is smaller. And so we can say for a point source, I is the power over 4 pi r squared, which is the surface area of the sphere. And so we see that as we move further away, the sphere expands as it propagates, and the same power is being spread over a larger and larger area. And so the intensity drops. And this makes sense with what we know. If you're very close to bright light, it's very intense, but as you move further away, the intensity drops. And it falls off as 1 over r squared, assuming you're dealing with a point source. If, on the other hand, you are dealing with what we call a collimated beam, that is a beam that just travels in a sort of narrow cylinder, then the area that the energy is, that the power is spread over is just the cross-sectional area of the beam. And as long as the beam has the same cross-section, the intensity will not change. This explains why laser beams, for example, if they are focused and collimated properly, keep a fairly high intensity. Unfortunately, even the best laser beams, as long as you follow them far enough, they will start diverging and get broader and broader. But for a lot of applications over short distances, the beam width doesn't change very much, and so the intensity stays fairly high.